Good afternoon, everybody. I'm happy to see that such a nice turnout. I think it's testimony to Eddie's great talks he gave in previous visits. As you may know, Edward Farhi comes by to visit the Google LA office every few times a year to help with our project on quantum artificial intelligence, which actually I was thinking at some point we should give you an update on how this is going, because this field has come a long way. Actually, some people of you, they may not know, if you go to our rooftop and look in this direction towards the Information Sciences Institute, there's actually the first commercial quantum computer is installed there, which is actually based on the computing principles that Eddie invented. But this time, or it has become tradition that whenever Eddie comes through, he, for cultural enrichment, will give a big physics talk. And today we'll talk about the Higgs Boson, and as many of you may have seen in the news, there's some maybe, yes, no evidence that the Higgs is being discovered in the Large Hadron Collider. And Eddie will talk about this today. Maybe many of you have seen him before, but for those who don't know, Edward is the director of the Center of Theoretical Physics at MIT. Eddie.
Okay, thank you. Okay, well, thanks for having me. Okay, so I'm going to adapt this talk as I go along based on what I feel the audience knows about this subject. So we'll see how it goes. So thank you for having me. So I'm going to be talking about the Large Hadron Collider and about the Higgs Boson a little bit, and why it's important or interesting to us in physics to know about the Higgs Boson. Now, so we're first going to talk a little bit about the Large Hadron Collider, and I'm only going to have slides about the Large Hadron Collider because there are pictures and we can visualize things. Once we get to the theory end, it's going to be much harder to visualize, so I'm going to drop the slides. Otherwise, I could just assault you with giant equations, which I don't think you want to see. So I'm going to try to talk about the Higgs Boson without visual aids. We'll see how we do. There is always the blackboard. In 2008, I think it was September 10th, 2008, the Large Hadron Collider announced that they had collisions. And that was the turn on of the Large Hadron Collider. Of course, they had turned it on before, but that was the official announcement. And this was the Google website on that day. So Google acknowledged it by turning that into their, what do you call it? The home page, the front page.
Google Doodle.
The what?
The Google Doodle.
The Google Doodle. Okay, I didn't know that. I'm not an insider. And of course, that was a big deal. Now, for those of you who don't, I'll just help you a little bit with what the Large Hadron Collider is. The Large Hadron Collider is a machine that collides protons on protons, and these protons go around in two rings, which are going in opposite directions, and then the protons have enormous energy. I can tell you how much energy they have in a minute, and they collide at a number of collision points, and what happens at those collision points is the debris from the collision goes showering out, and that gives us information about elementary particles at the most fundamental level. But the Large Hadron Collider, oh, what happened?
Just logged out.
Oh, logged out because we weren't touching it enough? Okay. It's a good thing you're here. Okay, so just to give you a sense of the scale, now it didn't go down. Oh yeah, there we go. You press the space bar. Okay, thank you. So that's to give you, that is an aerial view of, well, that's not an aerial view. The collider is underground. So that just shows you the size of it. This is the edge of the airport in Switzerland, and this is 27 kilometers around. So this is the largest scientific project ever built. And so this accelerator sits underground, and it straddles the French-Swiss border. And the little circle in there is a little pre-accelerator that's then used to get the protons up to even higher energy, where they go in counter-circulating rings to collide. Oh, let me just make another disclaimer here. I'm a theoretical physicist. I don't really know too much about how this thing works. It's sort of, you know, so I have a gee whiz attitude towards it. I know about as much about how this works as I really know about how my television works. You know, I kind of know, but really, if you pressed me, I don't know the details. But I do know something about what the results mean. So there it is. It's very massive, and inside is a tunnel, and there's me in the tunnel. I got to take a tour. So that proves that I'm a real physicist, because I got to go underground into the tunnel, and that's the actual Large Hadron Collider, where I got a tour. You can only go in there when it's off. You can't go in there when it's on. You would be fried if you were in there when it was on. So, and yeah, where's the switch? Yeah, I don't think it'll go on if there's a person in there. Yeah, but it's actually, there's a huge, the amount of energy that's carried in those beams is absolutely enormous. You know, it's, and the energy that's carried, these are two beams of protons, and, you know, I think it's the energy, it's like, it probably has the energy of a missile. And that in itself is not so impressive. Lots of things have the energy of a missile, like a missile. But what's amazing, you know, is that it's all carried by very few particles. So you have very few particles which are moving at very high energy. So the individual energy of the particles is enormous. And that's what we're interested in here, is colliding together particles with tremendous energy.
The particle traveling through the, where you are? Or
yeah, it's doing through that thing. No, it's in a tube,
okay.
And it's being bent by magnets, and those magnets have to be, the strength of the magnets, these are, you know, magnetic field bends particles, so you have to put these particles in a magnetic field to bend them. But the reason the accelerator is so big is because you want to get them to bend as much as possible, but the particles are really energetic. So to bend them, you need very big magnetic fields, because if you remember your elementary physics, you know, the faster you're going, the harder it is to bend. And these magnets are operating at such so intensely that they're practically shearing the metal that's holding the magnets together. And so if they increase the strength of this magnet, that thing would rip apart. So these are the most intense magnets, and there are 27 kilometers of them. And in order to get the magnetic field so high, they need huge currents, and those currents are maintained by using superconducting coils. So the whole thing is supercooled. It operates at just a few degrees Kelvin. It uses half the world's supply of helium just to keep it at that temperature. And, you know, it uses, and just to keep the thing running, it uses, you know, the energy of a city. It's very energy intensive, and it's just to collide together these particles.
So what's the temperature in this tunnel?
You mean where I'm standing there? Oh, I think room temperature.
But later. When
No, the magnets, I mean, all that supercooling stuff is all in that stuff on the left. Yeah, no. I believe it's room temperature. I'm not really sure. But I mean, the really cold stuff is all in that stuff to the right in the picture. Yeah?
How much mass do these particles have?
Okay.
Times their normal mass?
Well, okay, that's a great question. He's asking, you know, how much, some of you know that in relativity, that people sometimes talk about the mass of something increasing because it's going faster. We usually talk about that as the energy of the particle. So a proton, in units that I'm going to talk about in a few minutes, a proton, its rest energy in some units, which I'm going to use throughout this, is, we use what's called GeV. That's 10 to the 9 electron volts. That's the energy an electron would get if it crossed through a billion volt. You know, if you had a billion batteries and you moved an electron, a billion 1-volt batteries, the energy an electron would pick up is a GeV. That's about the rest energy of the proton. That's the rest energy. Now, these beams are at, the design is a little higher, but presently the beams are at 3.5 TeV. And a TeV is 1,000 GeV. So in other words, these things are their energy is 3,500 times their rest mass. It's 3,500 times the rest mass. And that's a huge energy. If you look at, let's say, an atom bomb, and you say, what's the energy released? That's a fraction of the rest mass of the particles. In an atom bomb, you have GeV nuclei, and there are MeV, which is million of electron volts released. So, these energies are huge by the standards of nuclear physics.
How high is it designed to go?
It's designed to go twice that. The total, it was 3.5 GeV, excuse me, TeV, I misspoke. It's 3.5 TeV per beam now. That's a total of 7, and it's designed to go to 14. And the reason they haven't gone to 14 is, some of you know that after it was turned on, there was an explosion because there was a bad solder. There was just a bad some little place in this whole superconducting wire where there was a bad joint. And suddenly this huge amount of current had no place to go, and the thing exploded. And that set the project back by about a year. But they're now beyond that. And the thing is running, and that's why we're talking about it now. So after the startup date, which I showed before, there was a setback, and now the thing works well. So the LHC works well, but it's not at its full energy because they wanted to be cautious about going up to full energy, because higher energy means more stress on the machine. And so it's running at half its design energy. But let me say one other thing about that. See, there are really, when you collide together particles, you collided together protons on protons, and you want those particles to interact. And there's only a certain probability that a certain interaction will take place. So if you have a fixed probability of interaction and you want to get events, you have to do that by increasing what we call the luminosity. You have to have the beams have to be intense, so that you have a lot of particles seeing a lot of particles, and therefore the actual probability of getting an event of interest is higher. So the crucial thing is not just the energy, but what we call the luminosity, which is I could define it. It doesn't matter. It's the number of particles per unit area per unit time. I just defined it. You need to get that high, and that means you have to be able to really focus the beams. And so here you have things. These things are moving. To get a relativistic energy factor of 3,500, you have to be going at 99.99999% the speed of light. I may have that off by a thing, but roughly 99.99999. I don't know how many nines percent the speed of light. So these things are really moving, and they're like the beams are like tiny needles, and they're going at the speed of light. You have to hit them head on, and otherwise you don't have the luminosity. And so what happened with the LHC is, even when they achieved the energy, it took tuning to get the luminosity up. And this is an art. To tune a machine like this to get the luminosity up, that's an art, and that takes time. But if you looked at the luminosity curve as a function of time, it really has shot up. And so after it turned on, the luminosity kept increasing and increasing, and now the luminosity is at the point where experiments can function. So in that sense, it's not only, it's at half its energy, but it's close to design luminosity, and therefore it works. And it's a huge technical achievement to just get the accelerator to work. But now, when these particles collide, so you have these protons and protons, they come together, and they come together at places called at intersection points. There are 4 intersection points at the LHC. And the 2 big ones, which I'm going to emphasize, which I'm going to talk about, are 2 of these points. There are giant detectors. One is called CMS, which stands for the compact muon solenoid. And the compact is a joke, because you'll see how big it is. And the other one is called Atlas. So these are the 2 things, CMS and Atlas. Those are their names. And these detectors, what they do is the particles come together, the protons, and they collide. And after they collide, they make stuff. They make other particles, and those particles shower out. And they have to be picked up by giant detectors, which track the particles through the detectors. And then what they try to do is, so first they have to do is they have to track what comes out. And then they try to use the tracking of what comes out to try to recreate the event that occurred and try to deduce something about fundamental law. But the first thing you have to look at is the detector to see what does it look like. To understand the collision, first you have to see it. So there's a giant detectors are built. So let me show you pictures of the detectors. This is just gee whiz stuff. So that's an example of the detector. Now look at the person. Can you see the person in the bottom of the picture? So this thing is enormous. And this is before the thing has been locked up. So this is the two halves of the detector are separated, and it's going to be then squished together. And I don't have a pointer, but you can kind of guess that the collision is going to take place about there. And then what happens is after this thing is locked up, is the particles will fly out. But every centimeter of that thing is a precision detector. It's been precisely built with silicon, with wires, and that can study the outgoing, what comes out. And these things are I would guess these are the most complicated things ever built. It's hard to imagine anyone has built anything technologically as complicated and as sophisticated as these devices.
What are all the layers doing there?
Oh, well, the layers are, I don't want to explain it too much because, first of all, I'm not an expert, but what they're doing is they are detecting various attributes of the outgoing particles. Some of them look for energy deposits. Some of them track the particles' curves. They're all, each layer consists of, see what happens is the particles fly out, so you want to have a picture, you want to make a track of where it went. So the particles pass through successive layers, and as it goes through the successive layers, there have to be detections. So that's why it's like an onion. And as the particles go out, it goes through successive layers. And we'll just show some more gee whiz pictures. Here's another picture of what it looks like. But each of these things, if you took one of these elements and you took it out and I put it there, it would look like the inside of your computer. And this thing is that big. So these things, these detectors, they, if you look at a paper by the groups that make these things, typically there are 3,000 PhD physicists on this thing, plus there are engineers and support staff. So when papers are published in this field, there is a 3,000 person author list. And to rise to the top of that collaboration requires skills that those people could run armies, and they takes very special skills to, you would not want to be in a fight with the leader of CMS. These people are very skilled on a lot of levels because you have to coordinate this. So there's another gee whiz picture. And here's another one of the side of it before it was being assembled. And this one is Atlas. That's the other giant detector. Again, this one is bigger than the other one. This has like more iron, I think, than the Eiffel Tower.
They're designed to detect.
No, they're designed to detect the same things. And therefore, there's another picture of it. Look at the size of the person. Here, there's the person. So these things are astonishing. So, if you ask me, what's really going on in there, I don't really know that well. So these things are now closed. The pictures are only good before it's locked up. So this is now sealed up. And you could just imagine the engineering feat just to assemble it and to make sure that the whole thing could fit together. It's impressive. What can I say? Now, but why do we bother? That becomes the next question. Let's see if I have any more pictures. Oh, yes. So now there's a collision. Now, this is that's sort of a representation of the collision. And what happens after a collision is there can be thousands of particles streaming out. And this is some kind of graphical representation of what's been read out. Now, the other thing I should say about, one second and I'll answer your question. One thing I should say is that when the particles collide, there's a collision. Now, there's so much data being generated by these collisions that it all cannot be read. the data stream is too intense. The data coming out of this, the data stream is, like all the cell phone conversations in the earth, something like that, constantly. And they cannot read all the data because there's too much of it. So what they have to do is they have to do what are called triggers. And a trigger is you look at an event means a collision, and you have stuff coming out. And you look at the event, and then you ask a question. Does it have a characteristic that makes it worthy of keeping the event and reading it to tape, they say, of storing it, or should we pass on this event? Now, that's if you don't know what you're looking for, because you want to explore unknown physics with this device. So if you don't know what you're looking for, and you have to make a trigger, well, that's a scary proposition, because you may be triggering on the wrong attribute of interesting physics. So, there's a whole discussion of how do you set your triggers. But they cannot record all the events. There's too much stuff coming out. The data and the numerical analysis, the data analysis is beyond what could possibly be done.
Do you have any of the numbers, like how many events per second, how many gigabytes per event?
I don't know. I don't know those numbers. That's just not my job. I just don't know.
But the beams do create many events.
Many events, because each beam contains many protons. Oh yeah, no. So there are, I think, the bunches of beams come every. I think the bunches are spaced by nanoseconds, and the bunches are spaced by nanoseconds, and then each bunch produces, I don't know how many events. I just don't know. You see, that's the kind of question they would ask me at Google, but I don't know. Just all I know is it's on the edge of what can be handled, and there are vast computer operations here attempting to analyze the data, and everything is done with special purpose code. Yeah.
How often do they run the experiment?
The experiment, okay, when it's on, it's running 24 hours a day. So when they turn it on, it runs 24 hours a day. But then there are definite breaks when they shut it down for maintenance. And for tune-ups. Because this is a very complicated thing. It's like a race car. You just can't run it 24 hours a day, 365 days a year. It's got to be shut down sometimes and tuned. So it ran, what's important to know is it's run long enough in 2000, at the end of 2010 and 2011, to collect a reasonable amount of data. I think it's now ramping up again. It then went into some scheduled shutdown. And it's going to go into a year-long scheduled shutdown in about a year. And in that year-long scheduled shutdown, they're going to raise the energy to the 14 TeV. Okay? So that's just, and what this is only supposed to represent are these dots are like firings of detector elements which are being recorded, which are then, of course, there are numbers associated with all this stuff to help reproduce the event. This next picture I have, I believe, is actual. That may be simulated data. This is an actual event, but shown by CMS in some way that, I don't know precisely what all these bars mean. They're scaled to some attribute of the energy deposit. But the data analysis problems here are huge. And you have to be able to pick out a tiny signal from huge amounts of data. Yeah?
So for each event, each pair of protons that collide,
Yeah.
it seems like it would be very difficult to track if there's a lot of events happening at the same time.
Yeah, that's right. They have to sort that out.
Which fundamental particles belong to that event?
That's right. That's right. They have to track that back. That's called, they have a problem with that. And that problem, of course, increases as you increase the luminosity. Right. So, yeah, they're at the point now, I think that's called pileup, when, they sometimes have difficulty distinguishing between different events, but somehow they know how to do it. They know how to separate the events. I don't know whether they do it in time or, I'm not exactly sure how they do
But by
it.
and large, are events happening like once every split second?
Oh yeah,
there are
they're
hundreds everywhere, and you just have to do some crazy signal.
Oh, I think it's much more than hundreds. I think it's hundreds of thousands per second,
Okay.
and it's because I think it's much more than hundreds. I think it's I don't know. I wish I should have looked up all these numbers. I should have figured you would ask me these things. But yeah, I don't know the numbers. it's enough, well, I guess it's enough that it's at the limit of what the biggest computers can and devices can process. I don't know if that sort of sets the scale of it. And the computing is done on large-scale computer farms spread out over the world.
And for each event,
Yeah.
I mean, what order of magnitude of subparticles are coming out of each event?
There could be hundreds to thousands of particles coming out of an event. Hundreds to thousands of particles. And then what you want to do is reconstruct something that happened. And, you know, I think Feynman described this kind of physics as you want to know what, try to understand a Swiss watch by taking two Swiss watches and smashing them together and then looking at what comes out, you know, and then looking at the debris and then trying to figure out, you know, it was made of we had a Swiss watch in there. It's kind of like that. So now what happens is that, you know, this is this field is divided between theorists and experimentalists. There are no people who are working on this who have the time and the inclination to actually get really deeply involved in theoretical physics, and there are very few theoretical physicists who work on these experiments. And to enter the experiment, if you were a theoretical physicist and you said, you know, I want access to everything, I want the data early, they would say you'd have to join the collaboration. And to join the collaboration, that means you have to work. They have to, you know, help build parts of the detector. You have to run shifts, which means you have to be in the control room while things are working. You would have to be responsible for things. So the field is very divided. I mean, probably the last great theorist who was an experimentalist was Enrico Fermi. And since Fermi, I don't think there's been another, you know, really great, Fermi was both a great theorist and a great experimentalist. But there hasn't really been another one since that time. This is just too complicated to have, well, to divide your time on. So the community is divided, and there are the theorists who try to speculate about what's going on and try to understand it, and there are the experimentalists who are really interested in the device and pulling the data out. Okay? So now we're going to talk about the Higgs boson a little bit. Now, you probably have heard, or I'm going to tell you, and I'm going to tell you more about the Higgs boson in a few minutes. We have something in elementary particle physics, which I'm going to talk more about, but as a prelude to that, there's a thing called the Standard Model. And the Standard Model consists of a list of elementary particles, which I will show you in a couple of slides, and of elementary particles. And it also, and those particles include quarks and leptons and the photon and a bunch of particles, cousins of the photon called gluons, the W and Z. Well, I just listed the whole thing. The leptons, the quarks, the gluons, the photon, the W and Z. And then there's one other particle which sits in the Standard Model. It's called the Higgs boson. Okay? But the Higgs boson had not been seen. And one of the goals of this device is to create the Higgs boson, and to create it in a fashion where it will be made, and then it's very unstable. And it's made, and then it decays, and you want to see the debris coming out of the decay and say, we made a Higgs boson. Now, the theory, which I will talk more about, says that the Higgs boson exists. And there's a lot of evidence for its existing because the theory, which I'm going to talk about, the Standard Model, is very, very successful. There's never been a prediction of the Standard Model that has ever been nullified by an experiment. So every prediction of the Standard Model is consistent with every experiment that's ever been done. But it has an ingredient called the Higgs boson. And that ingredient, the Higgs boson, its mass is not specified by the theory. Its mass is an unknown parameter. So when you're looking for the Higgs boson, you don't know its mass. So that means that it makes it harder to know exactly how to look. Now, the mass of the Higgs boson affects the way it decays, because particles can only decay to things lighter than themselves. That just follows from simple conservation of energy and momentum. If you go to the rest frame of something and it decays, you can just figure out quickly that it can only decay to things lighter than itself. So when you make a Higgs boson, it's got to decay into stuff that's lighter. And what that basically means is the heavier the Higgs boson is, the more channels it has to decay into. And since there are more channels, it's easier to see. So a light Higgs boson is harder to see than a heavy Higgs boson. So with the amount of data they have been able to make plots like this. I'm only going to roughly explain what these plots are. But it gives you, let me give you an analogy to what you do with your fixed data. Suppose I told you I have a coin, and it may or may not be biased, but you don't know how much bias it has. So maybe it's a 50-50 coin, or maybe it's a 60-40 coin, or maybe it's an 80-20 coin, or maybe it's a 99-1 coin, okay? Now you flip it 50 times. Let's say you flip it 100 times. You flip it 100 times, okay? And you get 53 heads and 47 tails. Well, it's probably not a 99-1 biased coin. That would be very unlikely. But maybe it's a 50-50 coin. Maybe it's a 60-40 coin. So with a limited amount of data, you cannot analyze certain possibilities are less likely than others. Does that make sense? So, if you can only do 100 coin flips, you're not going to have a 99-1 biased coin if you get 53 heads. I mean, it could happen, but it's extremely unlikely. So what these plots represent is this plot, on this axis is the Higgs boson mass. The reason I'm showing you this is real data. So this is the Higgs boson mass. This comes from CMS, but this includes all the data that has been taken up through about a couple of months ago. So that's data which has been analyzed. The units here are inverse femtobarns. A barn is a unit because it has to do with how big something is, and the unit is the size of a barn. So the side of a barn, you want to say something big? Yeah, it's as big as the side of a barn. So anyway, these are inverse femtobarns. And anyway, so as a function of the Higgs boson mass, this is data. And this is data. And what this data is supposed to indicate that if the Higgs boson were produced there's a certain expectation for how much the Higgs boson should be made, but you can't really be sure. Oh, I should say one other thing, excuse me. There's huge background here. Okay, let me go step back 1 second. I forgot to say that. When you make a Higgs boson, it decays into stuff. But there's a lot of other processes which are making decay particles which look like that. So there's background. The Higgs boson signal sits on background. It's not a unique event that, poof, you see a Higgs boson. It's a signal, and it sits in a sea of background, which can mimic it. Okay? So what you have to do is you can say, as a function of the Higgs boson mass, how confident can I be that we would have seen the Higgs boson if its mass was, let's say, 300 GeV? And without explaining it, if you're below the red line, it means you didn't see it. So they have been very confident now that the Higgs boson, most of this stuff is way below this line. Remember the GeV? That's the unit I told you about. 1 GeV is the rest energy of the proton. So they can be very confident that the Higgs, is gone. It doesn't exist between 140 and 550, because most of this stuff is really below the red line. But there's a little upward fluctuation here. And there's a little upward fluctuation. This is expanded, a little upward fluctuation, but it's not really a huge fluctuation. And this is from CMS, and the other Atlas, which is the other detector. Here's a similar type plot. Same amount of integrated luminosity means stuff absorbed. Remember I told you the energy was 7 TeV, because that's the total center of mass energy. This is all the 2011 data. And there's a little upward fluctuation here, this blue thing at about 125 GeV. The only trouble with this little blue thing is one channel. It's called gamma-gamma. That means 2 photons. Now, so what's happened is that there's an upward, the Higgs boson has many ways of decaying. So you would expect that if you make it, you would see it in this channel, but you would also see it in other channels. So this is the one where the signal is biggest. They happen to see an upward fluctuation in gamma-gamma. That gamma-gamma is the same as 2 photons. Physicists call photons gammas. So there's an upward fluctuation, but there are not upward fluctuations in other channels. So the whole combined effect, including what's called the look elsewhere effect, because if I tell you that I'm looking over an enormous number of masses, and I say, what's the chances that there's an upward fluctuation? Well, there's always a chance that there's an upward fluctuation somewhere. So if you take into account look elsewhere, and you combine all the data, it's a 3 standard deviation effect. That's basically what it is, 3 standard deviations for the observation of the Higgs boson. So that is not a huge signal, just 3 sigma. So they are not claiming discovery. They are only saying that they're seeing the hint of a signal. I'm showing you the data, not that I expect you to understand it, but these are summary plots from ATLAS and CMS, and okay, we'll talk about that in a minute. So is it, so can we say the Higgs boson is there? Let's talk about that for a minute. Would I say it's there? I would say yes. I'll tell you why. First of all, I believe the Higgs boson's there because that's the most likely explanation to fit the standard model, is that there is a Higgs boson. Second of all, the Higgs boson, remember I told you it exists as part of the standard model. So because it exists as part of the standard model, its mass is a parameter in the standard model. And you can calculate processes in the standard model, certain other decay rates and certain other things. And you can then measure those other things, and you can try to fit the mass of the Higgs inferentially. So this was direct detection, but you could say, given the fact that it's a parameter and it affects other things, let me go measure those other things and then fit for the Higgs mass. Okay? So if you do that, if you fit for the Higgs mass based on existing data other than this, you find a value of, I think, 80 GeV. The best fit value is 80 GeV. Now, it was known that the Higgs boson had to weigh more than 115 GeV because of other direct detection measurements which had taken place. Okay? So now I tell you, you have a parameter, and the best fit value is 80. But I know it has to be above 115. What do you guess for its value? 116? I mean, that would be your best guess, right? Because you want to be as close to the fit value as possible right at the edge of the exclusion. Does that make sense? So, the best guess is 116, 120, low, based on the previous, low I mean not 500, because 500 is way away from 80. So, there was even before this, there was a notion that Higgs mass is probably not much above 115. It's been excluded from that other picture I showed you. It's really excluded above 140. Everybody thinks the Higgs is there, and suddenly you see an upward fluctuation. So what would you conclude? Well, my conclusion is if the Higgs boson weighs 125 GeV, they saw it. I don't know. Is that?
So can I ask
Yeah.
what the best fit that gave 80 and also the thing that said it had to be greater than 115, were these equations or were these data or what was?
Okay, no. The best fit that said it should be 180 is you take the Higgs. I haven't talked about the standard model. I'm going to do that in a minute. But we have an existing edifice that describes the interaction of elementary particles, and the Higgs mass is a parameter in it. So given that parameter, you can then say, let me look at other observables, other things that have been measured. How do they depend on the mass of the Higgs? So there are I don't know, maybe 100 things you could look at. And then you do the best fit to the mass of the Higgs on using not direct detection, but inferentially. And that gives you 80. The 115 came from previous accelerator experiments whose reach was as far as 115.
But what does it mean with these inferential calculations that it's not true? It seems like direct observation showed that it's above 115, but in previous calculations it was
No, because the best fit was 80. So that means that, if you're doing a chi-squared fit, and the best fit is at 80. So it's not as good a fit at 90. It gets a little worse at 100. It's terrible at 200. But, if I tell you...
It doesn't break the model.
No. That's right. Above 200 would be trouble for the model. Right. Given the statistics, the weakness of the statistics, 125 is still acceptable, but 200 is getting to be, would stress the model. The model would be stressed.
Like a standard deviation around the 80, right?
Yeah, that's what I'm saying. I don't remember the number. Yeah, that's right. There's a standard deviation around the 80. The 80 is the central value. And, maybe the standard deviation around the 80 is 20 or something. So, a couple of standard deviations away you can tolerate, but 10 or 20 standard deviations would be nerve-wracking. So is the Higgs there? I don't know. And I don't think the experimentalists know, and nobody is sure. They're not claiming observation, but they kind of think they've seen it. They're in a tough situation, and the only thing that's going to improve this is more data taking. It's just statistics. It's just the name of the game is statistics. If the LHC continues to run well, the statistics will improve, and it'll just be a statistically more significant observation. Okay? So that's sort of the background on where the experiment sits. As of now, again, it's turning on. I think it's running now, but the data taking will take again, will go on, and the expectation is if it continues to work well, then in about a year, the statistics will have improved significantly enough that they'll be able to make definitive statements. So it's a huge investment of time and energy to get, this kind of weakish signal. But, they're doing the best they can. So now I want to talk a little bit about this is a slide I stole from a colleague. That's why it has his name on the bottom. This is a picture of the elementary particles as far as particle physics is concerned. We all know that the world is made of atoms, and inside of atoms are electrons, and then at the core is a nucleus, and the nucleus is made of neutrons and protons, and inside the neutrons and protons are quarks. And our most fundamental understanding of elementary particles has quarks, which we'll talk about now. The quarks come in 6 varieties, which we call flavors. And the flavors are called up, down, charm, strange, top, and bottom. Okay, those are just their names. I don't know how they got those names. Doesn't matter. They're just names. Up, down, strange, charm, top, and bottom. Now, the up, charm, and top quark all have charge 2/3. And when I say 2/3, I'm working in units where the proton charge is 1 and the electron charge is -1. Okay, so they have charge 2/3. The down quark has charge -1/3, as does the strange quark and the bottom quark. So those are the quarks. And one thing that's really interesting, this gives the mass of these in GeV. So the up and down quarks weigh about 10 to the -2 GeV, that's about 10 MeV. Remember, the proton weighs 1 GeV. And we are made of up and down quarks. Inside the proton are 2 up quarks and a down quark. That the charge is 2/3 plus 2/3 minus 1/3, which is 1. And we're all made of up and down quarks. But the up and down quarks are very light compared to the proton mass, and that's because the proton is held together by other particles called gluons, and the proton is made entirely of binding energy. The mass of the proton does not come from the mass of its constituents. It comes from the interaction of the constituents. And but what's very odd is that the up quark weighs between 10 to the -2 and 10 to the -3 and 10 to the -2 GeV, and the top quark happens to weigh 175 GeV. So the top quark, remember, the proton weighs 1 GeV. So at 175 GeV, that's like the weight of a nucleus. That's like the weight of, I don't remember my chemistry well enough, whose atomic weight is 175. Somebody up there in the periodic table. So there's a quark, okay, which looks just like the up quark, which weighs as much as more than 175 protons. Proton mass is actually 0.938 GeV, but anyway, let's call it 1. So it weighs like 175 GeV. And accordingly, the bottom quark has a friend, the strange quark, and the down quark, which we're made of, has a friend, the strange quark, and the bottom quark. And the bottom quark weighs 5 GeV. So we have a quark, a charge minus the third quark, that weighs 5 times what the proton weighs. In addition, we have the electron. The electron weighs 500,000 electron volts, which is a million remember, the proton mass I said is 1 billion electron volts. The electron weighs 500,000 electron volts. And because I say weigh in mass, because I set C equal to 1. You know, E equals mc squared, but if you work in my units with C equals 1, energy and mass have the same units. Okay, I can't not do that. That's just that would be the hardest thing for me, to live in a world where C was not 1. So I'm forced. Mass and energy have the same units. I can't help that. Okay, because C is 1. So that's just units. Okay, so anyway, in my units, mass is measured in energy units, and it weighs 500,000 electron volts. But it has a friend called the muon, which weighs about 100-something million electron volts. And there's another guy called the tau, which weighs 1.5 GeV. So note there are 3 electrons. These guys are very much alike, the electron, the muon, and the tau. There are 3 particles which are alike in all respects, except one is heavier than the other and heavier than the other. Now, why are you familiar with the electron and not with the others? And there's a very simple reason for that. The electron is the lightest charged particle. Okay? Now, if you believe in the conservation of charge, which of course you do, then the lightest charged particle has to be stable. Because if to decay, you have to decay into something lighter than you. And if there are no charged particles lighter than you, then you're stable. So the electron is just stable by accident. It happens to be the lightest charged particle, so there's no place to go. So, but from a particle physics point of view, that's not that interesting. It just happens to be stable, which is a very good thing if you want to make people, you want to make stuff, you want to make it out of stable particles, but its stability is sort of, you know, an oddity from a particle physics point of view. It just happens to be stable because it's the bottom of the chain. But other particles can decay into it. It's just got nowhere to go. And so, you know, we're very familiar with certain particles which are stable or almost stable, like neutrons and protons, because for similar reasons. Well, the neutron isn't even stable, but let's say the proton is a stable particle. It may not even be stable, but anyway, let's let that go. It's stable enough that you can make stuff out of protons and neutrons. And so, you know, we're familiar with certain particles, but from a particle physics point of view, that's not fundamental. And all these particles are equally interesting. And so there are 6 quarks, and there are 3 leptons, they're called, which are friends of the electron. Oh no, there are 3 more. There's the 3 charged electrons, and then there are 3 neutrinos called the electron neutrino, the muon neutrino, and the tau neutrino. And these are known to have very tiny masses on this scale. In fact, they're of order an electron volt or less than an electron volt, which is 10 to the minus 9 GeV. So we have these other particles. Now, what's really strange here, I'm going to now reveal to you the biggest mystery in particle physics, okay? It's this disparity in mass scales. It's completely not understood. Why it is that there are elementary particles in nature which seem similar in many ways, but have radically different masses. You see, it's very, very hard to understand that. If you imagine that things are composite, like if I said to you, you know, why does helium weigh twice, you know, when you go up the periodic table and I look at the masses, you know, how can I understand that order? Well, it's pretty simple, because once you realize that elements in the periodic table are made of constituents, if you have 3 neutrons and protons, you probably weigh about 3 times what something with 1 proton weighs. If you have 10, you weigh 10 times. And you get a pattern. It makes sense. It's not so mysterious, the pattern of masses, once you understand they're made of constituents. But here we have mass disparities between similar objects, the top quark and the up quark, where the mass disparity is, I think it's a factor of 50,000. The disparity between the mass of the electron and the electron neutrino is a factor of, I can't even get these numbers right, some big number, millions or billions or something, right? Some crazy amount. Yeah.
So you have particles, that's an elementary particle, the top
Yeah.
quark.
Yeah, there's nothing, it's not believed to be made of anything.
How have we seen it? Like the world
Because it gets created in collider experiments, it decays, the debris from the
So
collision is then reconstructed to see the particle.
When it collides, it actually sort of bumps particles together to make a bigger particle.
Right, I didn't really say that too clearly, right. So what happens in the collision is the energy, you see, you know that E equals mc squared, and you know in the atom bombs that you take mass and you make energy. Here we're going the other way. We're taking the energy of the beam, of the particles in the beams, and we're colliding together to make new forms of matter.
And then they decay pretty quickly?
Oh yeah, these decay in what's called a jiffy, which is, you know, it's about 10, I think a jiffy is 10 to the minus 24 seconds. Some very fast amount of time, yeah.
These other particles up there with the same kind of energy that Higgs is supposed to have, why are they so much easier to
Oh, just because of their decay characteristics, right. That's a great question. Everything else in this diagram has been seen, and it's just a question of what are the characteristics of its decays that make it amenable to detection, and what are the production cross-section probabilities. It's just characteristics of these particles. Of course, these particles up here could never have been made until we had accelerators capable of reaching these energies. But you're asking a great question. It looks now like the top quark weighs more than the Higgs. But the top quark is discovered earlier, and that's because the method for production is just more amenable to detection. And its characteristics make it more amenable. So the Higgs boson, well, I mean, it may be a little high here. I mean, maybe it should be down a little bit. I guess there are a couple of other particles I didn't mention. There's the photon, which is massless, and the gluon. The gluon are the particles that carry the force between quarks and are responsible for the binding of quarks together to make protons and neutrons. They're called gluons, you know, very witty.
What is the horizontal position? Like the muon, why is
Oh.
that below the strange?
Oh, yeah, well, that's a great question. What is this position? Okay, well, this one is a separate column. These things are grouped in generations, and this is, in some sense, an arbitrary grouping. It turns out there are 3 electron-like particles. There are 3 neutrinos. There are 3 down quarks, and there are 3, what I mean by down quark is charge minus the third quarks, and there are 3 charged 2/3 quarks. So there are 3 of each. But they kind of form sets of 4 because the up quark likes to decay to down quarks and electrons like to decay to electron neutrinos. But there is some arbitrariness in this. That is a kind of attempt at a periodic table structure by just grouping the light ones. You somehow or another you want to put the lightest ones together and then the next lightest, and those are called generations. That's a very arbitrary grouping, but it's one that physicists use. And there seem to be 3 generations and not more. We know there is not another generation.
That's not arbitrary. It seems very coincidental, except the ratios are all roughly equal.
It's not that, the ratios are kind of, you can do numerics with that, you can play games. The pattern of elementary particle masses is a complete mystery. There's no understanding of it, 0. And I've been in this game for a long time, and say there's absolutely no understanding for why these particles have these masses. They're all input parameters. I'll talk about the Higgs and its relation to this in a second, yeah.
So if the Higgs is lighter, what benefit do you get by bumping up the electricity? Just more luminosity?
He's saying, why? Okay, that's a great question. If the Higgs is light, why do we have to go to high energy? It's because they're smashing together. If they were smashing together electrons, before I say that, because the proton is made of constituents, 2 ups, a down, and a bunch of gluons. So even when you smash together a proton and another proton, the actual things that are interacting are the quarks inside. And they carry much less of the energy than the total object. A lot of that energy is actually being carried by the gluons. And you need the quarks to fuse together to make the Higgs. So what's happening here is that the proton is a bag of quarks, and you have another bag of quarks, and they're hitting together. The constituents are interacting, and those constituents do not carry the full energy. They only carry a small fraction of it. So you need to ramp up the energy of the proton to get the constituents to have sufficient energy. Now, had this been a different type had you used electrons don't seem to be made of anything. That might have, you wouldn't have had that problem, but then the production cross-section for electron to Higgs is practically 0. Yeah, so that's, yeah, that was not, it's not, yeah, that, why go to 7 TeV when you're only producing something that weighs 125 GeV? And it's because of what I just said. Okay? So,
So the W and Z have been discovered?
oh yeah, everything's been discovered on that plot. Everything has been seen. Every single thing is seen except the Higgs boson. And
There's no neutrino for the final column?
No. The neutrinos are actually, all these particles here are fermions, which means they're spin a half. They obey Fermi statistics. And these particles are bosons, which means that they're spin 0 or spin 1. So they obey Bose statistics. So the neutrinos are spin a half. There's no, there's no friend to the Higgs. So the situation we're in is this. We have a mathematical description of the interactions of these particles. That mathematical description allows us to write down a set of equations which describe the interactions of all these particles. I probably should stop now or in a minute and then let people go who want to go, and then other people can stay and ask me more questions. Is that a good idea? So why do I do that? Because I get some people are asking. Anyone who wants to go and needs to go can go, and those of you who are interested can stay and ask me more stuff. Okay? Because I didn't, we're wandering a little bit. Yeah. Oh, so if they don't find the Higgs, in fact, I would say that from a theorist's point of view, the discovery of the Higgs, in some sense, is a disappointment. Because if you said to me, what do I learn? I now live in a mental world, as most of my friends do, where we imagine the Higgs boson exists, and it's just been hard to find. And the exact value of its mass is not too important to us. So if you take my point of view, I look at the equations of elementary particle physics. I presume the existence of the Higgs. I don't know its mass. And, it's probably not too far from 80 because of what we said before. So then, what changes in my worldview when it's discovered and has a mass of 125 GeV and it decays exactly as it should in the standard model? I haven't learned anything. And in that sense, it's a great experimental achievement. I don't mean to diminish it, because it's like it shows that our standard model is correct. But in terms of theoretical advance, I would say it's very minimal, quite honestly, because it just confirms a worldview which most people have already adopted. And so, for me, it would be much more interesting if the Higgs boson were excluded. If those turned out to be just statistical fluctuations, and they come back and they say, with 99.9% confidence, the Higgs boson does not exist between 115 and 500 GeV, or else we would have found it. That would be much more interesting, and that it would be, no one knows how to deal with that. And that would be great, because that would certainly be great, I think. I think this is sort of the boring outcome. And there's a whole other question here, which is, maybe the LHC will uncover something else. They're not just looking for the Higgs boson. We've only been talking about that today, because it's a lot to cover in one talk about what's going on at the LHC. The LHC is looking for a lot of other stuff that could be anomalous stuff, new particles which are unanticipated, particles which other people have predicted. Nothing has been seen, 0. But go ahead.
So the Higgs boson causes the other particles to have mass because of symmetry breaking.
Yeah.
Is there any intuitive way to understand how that works?
Not exactly. The question was this. Very often you read that the Higgs boson gives mass to particles, and because of symmetry breaking. Those are the right words. And let's see. You see, there is a description of the elementary particles in terms of an object called the Hamiltonian. It's like the energy function. But, I have to think about the Hamiltonian in relativistic quantum field theory. And so I'm just going to write something on the board, and we'll just live with it, okay? So there's going to be a term. If I have a term in this relativistic quantum field theory for, let's say, the electron mass, I'm going to represent the electron by a field. You don't have, this is E and E bar. These things represent relativistic quantum fields, and I'm not telling you what those are. These are functions of space. They're complicated things. But this relativistic quantum field called E, and there's one called E bar, which is the antiparticle job. This term exists in the Lagrangian. Okay, this is before the description of the Higgs boson. This is what Feynman would have said. But now we have a more modern language, and we have a thing called lambda E bar E times the Higgs boson. We have a different coupling. So this got replaced by the modern world, where we have a coupling lambda E bar E times phi. Phi represents the Higgs boson. But what happens is that in the vacuum of the world, so if I write down the quantum state for the vacuum of the world, and I write phi and I write vac, this thing is not zero. It has a value which we call V. So that means that this field, that's what he meant by that there's symmetry breaking, that this phi field has a non-zero vacuum expectation value. I'll tell you more about what that means if you want me to. But what happens then is if I plug this in here, this becomes lambda V E bar E, and the mass of the electron is now lambda V. So that's the way it works. Okay, that's the way it works. The mass of the electron goes from a bare term to a coupling times the vacuum expectation value of V. But I should put a little lambda E here for the electron. Okay? Now, in the old days, I had the mass of the electron, the mass of the muon, the mass of the tau, all unknown, the mass of the top quark, all unknown. Now I have lambda electron V, lambda mu V, lambda tau V, lambda top V. So now instead of having no idea where these come from, I have no idea where these come from. And so when they talk about, the Higgs boson resolving the mystery of mass, I think that's oversold, because it just, it's true, though, that the coupling of the Higgs to the particle after it takes its vacuum expectation value is responsible for the mass, but finding the Higgs boson is not going to change anything about our understanding of what those masses are. I don't mean to be so negative about it. It's a great triumph to find the Higgs boson.
So say you find like an utterly normal Higgs boson with 6 sigma, and everybody's happy.
Yeah.
Where does particle physics go, and how do we ask taxpayers for more money to build that?
That's a great question. Well, that's a very interesting question. It depends on who you are. I said before that it would be much more exciting if the Higgs boson was not discovered, because then I, a theorist, would say, look, we don't understand anything. We have to go to a bigger accelerator, and we need a more powerful machine, and that's so great because we can't understand it. But now let's look at it from the point of view of the experimentalist. You've gone to Congress, we could talk about in America what happened to the superconducting supercollider, but you've gone to the world bodies and you've said, I need this machine to find the Higgs boson, and it's not there. Isn't that great? And then the world people said, and I want a new accelerator. It really depends on where you sit. From the experimentalist point of view, not finding the Higgs boson is a disaster, because they set out to find it and it didn't show up. So although that's the better outcome, it's a terrible outcome from the point of view of the experimentalist. So how you phrase your argument depends on where you sit. And so I think in a way, not finding the Higgs boson would be turned around as a failure of the machine, whereas I would see it as a success, because it would have excluded, it would have meant something's deadly wrong with the standard model. So it depends on how you frame it, but there are many other things going on in the universe cosmologically that have bearing on particle physics. Most of you know that when we look out in the universe, we only see, we look at all the matter out there, only 4% of the observed matter is made of this stuff.
There's the mysterious dark energy.
There's dark matter and there's dark energy. They're two separate things, right? There's both dark matter and dark energy. if you go out and you look at distant stars, and you say how much matter is, how much do I see? That's only a small fraction of the matter. Not a small. That's a fraction of the matter that there is. And in addition, there's dark energy. And these things probably have explanations in particle physics. So definitely the field continues to go on. But I would say that I would be unhappy if, from my point of view, if the LHC finds the Higgs boson, weighs 125 GeV, like you said, there's a big, the statistics is significant enough to be conclusive, and nothing else is found. It would be very challenging for me to know what to do. That's one of the reasons I work on quantum computing. Because I like to work on more than one thing, and it's very interesting for me to have another life.
So there's other things on here.
Well, I would have to say that, theoretical particle physics, experimental particle physics is already, you have to have a very special type of personality to want to enter a 3,000 person collaboration. And if they get larger or it gets more complicated, there are sociological effects of that. Certain people will just not go there. I mean, certain people want to work on experiments that are, they can control in a tabletop experiment or in a small lab. They don't want to work on a 3,000 person collaboration. So that's definitely something, and the amount of time it takes to do these experiments is very long, and there could be setbacks. I mean, I said that they will find the Higgs. Presumably, the thing will be resolved in a year. That's assuming everything works. Maybe there'll be another mishap, and the thing shuts down. So, from an experimental point of view, there are a lot of challenges about going into this field, but people still go into it, and they're very excited by it. From a theoretical point of view, I would have trouble really. I would say that if I were a young theorist now, I would concentrate on cosmology and looking for hints about elementary particle physics that come from cosmological observation. Because I think this is just getting very slow and very hard. Who paid for this? Okay, so this is totally paid for by Europe. CERN, this sits at a laboratory called CERN, CERN, which stands for Centre European pour Recherche Nucléaire, something like that. And there's a consortium of European nations, including Germany, France, England, who paid for it. But the United States pays big bucks for the detectors. And there are big United States groups working at both Atlas and CMS, and that's funded by the Department of Energy. So, and they pay both for the salaries of people to work there, and they pay for some of the hardware that goes into the detector. The detectors are big ticket items. They're billions of dollars. Those things I showed you, they cost billions, and the U.S. pays there, but the U.S. did not pay for the accelerator itself. And in high energy physics in this country, accelerators, this country's really turned against it. There was a proposal to build a machine which would have been more powerful than the LHC, called the Superconducting Supercollider. It was 50 miles around. They started to dig it in Texas, the tunnels for it, and it was set to go. And then, for very complicated political reasons, it was killed. This was in the mid-90s. And that would have been great. Had the superconducting supercollider been built, all this would have been done years ago. It would have been more powerful than the LHC. And it didn't happen. And now, if you look in the United States, Fermilab is shut down as a high energy, it's run. The Tevatron, which is the biggest ring of, it collides protons with antiprotons, that's been shut down. And Stanford Linear Accelerator Center is now not a particle lab anymore. It's a user facility where they shoot down, they use electrons, they do things to create beams of intense photons, which are used to study materials. So it's a user facility for material science. So this country has turned its back on high energy physics. And we better really watch it, because they're starting to turn their back on NASA too. Right? All these spacecraft things being unfunded, and high energy physics has a lot of trouble defending itself. We live in tough times, and it has a real bearing on scientific funding.
So you guys have like this problem, seems like, where the experimental evidence is explained by the current model pretty well, so it's hard to have this like big mismatches of model and things.
Exactly.
that need answering.
That's what I'm confessing to you. Yeah. At this moment, assuming that that little signal grows, then I would say that from my point of view, the field of high energy physics is just getting confirmed again. And but it depends on your perspective. It was really the late 70s and early 80s that the Standard Model was written down, where people wrote down the actual equations that describe the strong, the weak, and the electromagnetic force. Okay, that's 3 out of 4 forces in nature. Gravity is a little different, but that's pretty well taken care of by the general theory of relativity. So we have the weak, the strong, the electromagnetic force. We have these particles. The force carriers are listed: the photon, the gluon, the W, and the Z. Those are all force carriers for the weak, the electromagnetic, and the strong forces. Now, that theory was written down with 3 parameters in it: lambda E, lambda mu, lambda tau, lambda top, all these free parameters relating to the masses, and there are a few other free parameters which then get measured. And if you then take the experiments that allow you to determine the parameters, then you look at another experiment, say, I've determined the parameters, I'm going to predict another experiment. Okay? Everything works perfectly. There's never been a violation of a prediction made by the Standard Model since it's been developed. So since the early 80s, which is 30 years, the Standard Model has been reigning perfectly. It's never been contradicted. And this will continue in this vein. It's a kind of a strange place to be. We're very, very successful in elementary particle physics, incredibly successful. But on the other hand, even though we're successful, we lack deep understanding of certain things. Like, we don't understand the disparity in masses. They're just input parameters. And that's very unsatisfying. So most of us believe, no, I shouldn't say that, because there are people who believe in the multiverse, and people who believe in the multiverse think that there are other universes where these parameters just have different values. So, but I don't believe that, so some people believe that this is the end of the line for particle physics. These are random numbers, and they have about as much, you can understand them about as much as well as you can understand the Earth to Moon distance. What's the Earth to Moon distance? I don't know. It's what it is. Can you write down an equation that gives it? No. It's just some rock that ended up a certain distance from us, right?
Does the Anthropic Principle save us at all?
Not here. Yeah, the Anthropic. So then he's saying, does the Anthropic Principle, you could ask yourself, suppose I have the mass of the top quark, would suddenly, the universe, the world around us look different? I don't see how. So, yes, go ahead. When I say dark matter can't be seen, yeah. Well, dark matter, it can't not be seen. I mean, assuming that it has some interaction. When we say it's dark, it means it's not interacting electromagnetically. It's not glowing. But that doesn't mean that it doesn't have any interactions. So dark matter is stuff that is known to be out there, but it doesn't have, it may interact with another yet to be determined force, or it may interact with these forces but have very weak charges, so that the interactions are extremely weak. And it's possible that the LHC could make a particle which could then turn out to be the dark matter, but it doesn't, dark doesn't mean if it had zero interaction, if dark, except gravitational, because everything that weighs something, or even if it doesn't, anything with energy gravitates. So if you had sterile particles, meaning they have zero interaction other than their gravitational interaction, they would be very hard to find, and it would not be produced at the LHC. So I'm assuming that dark matter is not 100% sterile. It has some weak interaction. Well, I don't mean weak in the technical, not in that sense, but some not strong interaction. I mean, I don't mean not strong in that sense. What's the word for weak? Tiny interaction. It's possible, yeah. Mm-hmm.
When you're saying you're assuming that it has other interactions than gravitation, does this mean you're hoping, because otherwise it would be boring?
Yeah, it would be boring, yeah. Well, yeah, so for example, if dark matter turned out to, if there's another force, and that and you know, that yet to be discovered, which it lets it interact with stuff. That would be very, very good. Another force. Oh, but I wanted to finish my thought before about the success of the Standard Model. So, you know, since the 80s till now, we have this amazing thing where everything works, but there are mysteries. And people are very frustrated because they say particle physics is making progress. Well, it depends on how you look at it, right? If you go 300 years in the future and say, look, in the 1980s, you know, in the 1920s, they developed quantum mechanics. In the 1980s, they wrote down the full theory of the interaction of elementary particles. And it wasn't until, you know, 2029 until somebody figured out what the mass pattern is. You know, is that slow progress or not? It depends on how you look at it. These are some of the hardest questions in all of science. And, you know, just because we haven't broken them down since the 80s, I don't think means that theoretical particle physics is done, but I think it's really hard. Yeah?
So if those are all fundamental particles,
Yeah.
how do they decay?
Oh, well, each one is different. The electron, like I said, is stable because of the reason I said. But for example, like a top quark will decay to a bottom quark, and a tau and a neutrino. They decay to things lighter. There are these decay chains.
That itself is a fundamental particle. How can it decay to something else?
Oh,
is it just the energy state is changing, or?
Yeah, I guess it's just a name when I say a fundamental particle. I guess it's fundamental because it doesn't look like there's anything inside of it. Would that mean, I don't know how we're going to define fundamental. I mean, is the proton fundamental? It's made of quarks.
Right, yeah.
So probably would say these things don't seem to be made of anything.
Could they discover another, like that's not it for fundamental particles? Or?
Well, no, well, I could tell you for that. It's pretty interesting. We know there's not another neutrino. I can tell you how we know that. The way we know that is this. You see, when particles decay, when particles, if a particle can decay, that means it has a certain lifetime. And that means that there's actually an uncertainty in its mass. There's a thing called the time energy uncertainty principle, which says that if there's an uncertainty in how do I say this? Yeah, it turns out that there's a principle in quantum mechanics that essentially tells us that if something has a lifetime, which is not zero, so it has a width, it has a decay, it has a lifetime that's not zero, that its mass is not certain. And maybe I can make, well, I don't know if this is going to help, but it's sort of interesting. So if I look at if I want to, the Z boson likes to decay to neutrinos. The Z boson, it likes to decay to a neutrino and an antineutrino. It likes to do that. And it likes to decay to all that it can. The electron one, it goes to the mu one, and it goes to the tau one. It likes to decay. But it decays to other stuff too. And you can and you can make Z bosons by colliding together electrons and positrons. So there are colliders where you make Z bosons, and as a function of the energy, you can see this is energy, and this is sort of the number of Z bosons I make as a function of the beam energy in the collision. And what happens is the production cross section peaks at a value here, which we call the mass of the Z. In other words, you tune these beams, and the electron and positron come together, but when their energy, total energy, is exactly the mass of the Z, suddenly you start making a lot of Z's. Okay? But if the energy's off, you don't. But it's not perfect. There's a width to this, because if you're a little bit off from the central value, you still make them, but you make less. And this is called the width of it, gamma, the width of the particle, in terms of making it energetically. But that width is determined by its lifetime. That width is determined by its lifetime. So the faster the particle decays, the more narrow its width. Oh no, did I get that backwards? Gamma, yeah. So what that means is that by looking, if the neutrino decayed to another type, if there was another neutrino, odd, and it decayed to that would change the width. And so you can actually count the number of neutrinos by looking at the decays of the Z boson, and when they count the number of neutrinos, they get like 3.0 plus or minus 0.001, something like that. So you can actually infer that there are no other neutrinos. And there are other experiments, cosmological experiments, so you could be sure there are no other light neutrinos. So if there are no other light neutrinos, then it makes you wonder, well, if there's no other light neutrino, there are going to be more of these jobs. And then I could talk about other evidence for why there aren't more of these things. But it really looks like there are just 3 generations. Yeah?
So there's been a lot of accelerators built, a lot of experiments, like a lot of data produced. Is all the good stuff being squeezed out of that data already?
Oh, that's a good question. Recently Fermilab just went and looked at its old data and decided they had a little signal maybe for the Higgs boson around 125 GeV. There does, it's a great question. I mean, how do you, when I talked about that before, when you collide these particles together and you have this shower of data, right? And you're triggering it, so you may be throwing out stuff. So all you have is what you choose to read to tape, they call it. Now, if somebody very clever one day says, let's go back to that old data and let's reanalyze it. Let's plot X versus Y, where no one had thought of it before, maybe a new discovery will be made. The public wouldn't help you. In other words, I'm sure you could have, having access to this data would be very unhelpful because it's so complicated, the way it's binned, and you have to take into account all kinds of things like the acceptance of the detector. If you plotted the angular distribution of what's coming out, that's not the true angular distribution because the detector may be more efficient at certain angles. It may have a structural element blocking something at 23 degrees. So, the data is pretty meaningless unless you're totally immersed in the experiment. So, I think if you talk to someone in the experimental collaboration and you had a good idea, then, they would help you analyze it. But I think if you had access to the raw data, I can't imagine it would help you. It would just, I can't imagine. Yeah.
Does it matter whether the proton decays or not from a theoretical standpoint?
Absolutely.
Is there, what's interesting thing that would be explained if you knew if there one way?
If the proton decay?
The proton decay.
Oh yeah, well look. Well, first of all, the proton is the lightest particle made, it's made of 3 quarks. And quarks carry a quantum number called quarkness, let's say. And so if the proton, and quarks are always bound together to make things, so if the proton decayed, it can't decay, there's no other object lighter than it that has a net quark number which is not 0. So if the proton decayed, its quark number would disappear, and that means that there would be a conservation law would be violated. That would be like as big as if electric charge were violated. So it would be huge. But there are theories where people talk about proton decay. It would be very interesting if the proton decayed. But the proton lifetime, people believed, this is a great story, because people were convinced themselves that the proton had a lifetime of around 10 to the 30 years. Now, 10 to the 30 years is much longer than the age of the universe. So you could ask yourself, well, if it lives so long than the age of the universe, how am I going to see that? Well, you can see that if you have a lot of protons. Because if I tell you that the lifetime is 10 to the 30 years, that means if you have 1 proton here, the chances at 10 to the minus 30 it will decay in the next year. Right? A lifetime of 10 to the 30 doesn't mean it waits 10 to the 30 years. It means that in the next year, there's a probability of 10 to the minus 30 it will decay. So if you put Avogadro's number of protons, Avogadro's number is 10 to the 23. So if you take together, if you have 10 to the 7 proton, if you have 10 to the 7 moles of something, whatever it's called, you can get a lot of protons together. So people built vast underground detectors filled with material, and they waited to see proton decay. Because once you had a big enough volume of stuff, you could look for proton decay. And they went deep underground to do this because they wanted to be shielded from cosmic rays. So there are these amazing underground caverns where people have built giant detectors filled with fluids, and and around it are detector stuff, and they wait for a proton decay, and when the proton decays, they would see it. They never saw that, and the lifetime of the proton is now, I think, 10 to the 34 years experimentally.
At least.
At least 10 to 34 years experimentally. But those detectors deep underground, they saw neutrinos from a supernova explosion. Because in 1987, there was a supernova that went off, and when the supernova went off, it shot neutrinos out, and those neutrinos were detected deep underground. So suddenly you have this deep underground detector seeing a supernova go off on the far side of the galaxy. So sometimes you never know what you're going to find. But yeah, the proton is stable, at least its lifetime is, I think, 10 to 34 years, you seem to know.
No, I'm saying,
at least.
meaning we've never seen one decay,
Yeah.
or we have.
No, we've never
we
seen one.
calculated it
No, we've never
before.
seen one decay.
Okay.
Never seen a proton decay.
Okay.
Yeah.
Going back to saying if the Higgs boson was discovered, what its impact would be on, let's say, Maxwell's equations?
Nothing.
Nothing.
Maxwell's equations are contained in the standard model. And also the relativistic quantum field theory version of Maxwell's equations. I mean, it's not just, Maxwell's equations are classical equations, but Maxwell's equations are consistent with relativity and quantum mechanics. So the relativistic form of Maxwell, the quantum mechanical, Maxwell's equations are already relativistic, I misspoke. The quantum mechanical form of Maxwell's equations is part of the standard model. And that would be unchanged. Yeah.
So if the folks eventually found dark matter, dark energy,
Oh, yeah.
some way, do you think that it would just fit into the framework of the standard model somehow?
No. Dark energy and dark matter don't seem to fit.
So does that call it into question, or is it just this only applies to how these types of particles interact with each other?
There is no good explanation for dark matter and dark energy now, and I think that's one of the great questions. If you said, what would I work on, that's what I would work on. Try to understand dark energy and dark matter. But you have to have ideas. Yeah.
What engineering things might these be used for to be useful? Like, if we found the Higgs boson, what could we make? Or
Nothing.
Nothing.
You know, what can I tell you? They always say that, the World Wide Web was invented at CERN. By, guys, that's how the World Wide Web was invented by people trying to, get the computers at CERN to communicate. But, that's a spin-off. I should probably stop in one more question and I'll stop.
Yeah,
I'm good.
So to tie it back into the question that wasn't voted up, do you think the time travelers are going to sabotage the LHC again?
Oh yeah, the time travelers, yeah. Yeah, maybe the time travelers will stop. And next time I'll talk about time travel. Okay, thanks.
Thank you.